the question. How to, so here actually the question should be in this way. How to determine if two given functions are linearly independent or not. Yeah, we need to answer this question. Yeah. Given two functions, yeah. For example, sine, cosine. Sine, cosine, two functions. How do you check these two functions are linearly independent? Yeah. So we need to answer this question. Yeah. All right. Assume y1 and y2 are linearly independent. Yeah. Yeah. All right. Then there do not exist k1 and k2, two constants, such that k1 y1 function plus k2 y2 function equals 0. For all x on certain interval I. This is the definition of linearly independence. Definition. Yeah. Yeah. All right. So then, there do not exist. Yeah. So the other side, if there exists two constant, k1, k2, such that k1 times y1 function plus k2 times y2 function equals 0 for all x on certain interval I, then we say these two functions are linearly dependent. Yeah. Dependent, independent, dependent. Yeah. All right. Yeah. All right, so here on all. But here there is some little thing. Yeah. All, yeah. All right. All x on certain interval. Okay? Yeah. If for some points in the interval equals 0, some points in the interval not equal to 0. Okay? Yeah? It's different. Yeah, it's different. So here the definition is for all x on certain interval. Okay? For all x on certain interval. Okay? Yeah. All right. Now, we need to find a basis. Yeah, by reduction. Yeah, find the basis by reduction. Yeah, but at the same time, we need to see how to check if two functions are. Yeah. So here, reduction of order approach. Yeah, so there is a method here. Find the basis of solutions of the ODE for this equation. Yeah. So there is a method, reduction of order approach. Current ODE, the order is second order. Second order, relatively hard to solve. If we can bring down the order to first order, then it is much easier. Yeah. So the idea is, how can we find a way to bring down the order of this ODE? Yeah. That method. All right. Solution. To make that method work, we need to guess a first solution. Yeah. Sometimes hard, sometimes easy. Yeah. But here we want to guess just the one solution first. Yeah. Look at y1 equals x. So you can check. So double prime, gone, right? Yeah, x. You take double prime, it becomes 0. So the first term of the ODE, highest order term, it's gone. Then y prime is 1. So negative x plus x, y1, x equals 0. Yeah. So that is a simple solution. Yeah. If you can guess one simple solution, then there is some method we can use to bring down the order of that ODE. Yeah. Yeah. All right. Given the first solution of a second order homogeneous linear ODE, how to find the second solution? Yeah. Here, the second solution. Yeah. We need to use the first solution. We need to use the first solution to help us build the second solution. Okay? All right. Do a special substitution. We assume second solution y equals u times y1. U is a function. So ux. Here, you can also, we introduce a new function u that is the ratio of y over y1. Yeah. Y over y1. Whatever the ratio is, we just take that as u. Yeah. So here, u times x. Because when we take this form, we have a chance to bring down the order of the original ODE. Yeah. All right, let's do the calculation. Y prime, yeah, so this one. Yeah, also double prime, right? Y double prime, like this. All right, then we plug in the original equation and do some simplification. Yeah. All right, yeah. Yeah. After factorization, after some simplification, yeah, you can see, yeah, you have this simplified equation. All right. Then, yeah. So we try to write. We try to compare it with the original equation. We try to compare it with the original equation. Okay. All right. And here, yeah. So here, try to look at this equation. Although you have u double prime, u prime, but u double prime is the derivative of this u prime. Okay? Can you just treat u prime as a new function? If you treat u prime as a new function, double prime just first derivative. Your first derivative of the new function. Okay? Yeah. Let v equals u prime. Yeah. In this way, you bring down. Yeah. You bring down the order of the ODE. Yeah. Yeah, because the u term is gone. So the good thing is the u term is gone, right? Yeah. Yeah, because you use the original. Yeah. So you know cancellation, right? Here cancellation. So the u term is gone. All right. Then, so with that new v function introduced, now you can find the solution for this first order ODE. Yeah. Okay. Yeah. Yeah. Here we use O. Yeah. Yeah. All right. All right. Yeah. But here the separable, you need to, when you do integration, you need to use the partial fraction technique. Integral partial fraction technique. Okay? Yeah, here. Yeah. Partial fraction technique. Okay? Yeah. So here, decomposition, then you determine capital A, capital B, right? Yeah. Yeah. All right. So here I just write the decomposition result. Yeah. So then you take integral. Yeah. So you get you know, this one with absolute value. Yeah. Okay. Yeah. So absolute value. So there. Yeah. Because we need to consider. Yeah. So here, yeah. Remove absolute value. Okay. Remove absolute value. Yeah. All right. And yeah. So remove absolute value plus minus sign. Yeah. Yeah. So there. Yeah. Complete the solution. Yeah. Complete the solution here. Let me leave it to further explanation. Yeah. So here. You can think about it. You can try a little bit. Okay? Yeah. So I will complete the remaining part in the further explanation. Yeah. So here, this is part A. Module 2, part A. Okay? So I put it in the further explanation number 1. Okay? Yeah. All right. Yeah. Yeah. So mainly calculation. Yeah. For the calculation, we need to mainly I want to explain how to handle this plus minus sign. Okay? Yeah. Gracefully. Yeah. We don't want something very messy. Okay? Yeah. So we want to find a neat way to write our solution. Yeah. All right. Yeah. General process, reduction of order. Yeah. So the general equation. Yeah. Step 1. You need to find the first solution y. Yeah. 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 Guessing way many times it's too hard. Yeah. Yeah. So finding the first solution, yeah, you need some technique. You need some technique. Yeah. Okay? Yeah. Guessing most of the time you cannot make it most of the time. So then the first step, we need to apply some technique to find y1. Yeah. All right. Yeah. So suppose we find a y1. Yeah. So we can plug in. Yeah. So y1. Yeah, y1. Yeah. I missed the y1 here. The subscript. So I put 1. Yeah. y1. Okay. All right. Find the second solution with substitution. That's the relationship. Yeah. U times y1. y2 equals u times y1. All right. Then you do the calculation. Okay? Yeah. Prime, double prime, the calculation. Yeah. All right. Yeah. So here also y1, I think. Yeah. Because after we plug in, we won't have y, right? We have y1 or y2. So we. So that's 1. And yeah, because after you get that here, after you get this form, this last term is gone. Yeah. The last parenthesis term is gone. Okay? Yeah. After you cross out this one, then you have u double prime, u prime, then essentially it is the first order ODE. So after you introduce this v function as u prime, you just get a first order ODE. Okay? So you can solve this first order ODE. Yeah. Yeah. You know, with confidence. Yeah. And you go, yeah, so here, you know, yeah. Yeah. Solve it like that. Yeah. So v, yeah. So then v, yeah. So you can write a v in this form. Yeah. Okay? Yeah. V in that form. Then u equals integral of v. Yeah. Okay? All right. So your y2 equals, yeah, here. Yeah. Here. Yeah. Let me explain. So here you can see we don't include constant, right? Yeah. So when we write this V, we don't include constant. Here, another thing. So two things I want to explain. One thing, absolute value of V, absolute value is gone. Okay? We take V equals 1 over y1 squared times e to the negative something. Okay? Yeah? Reason why we can remove the absolute value without any constant, without any constant included. Yeah. The reason is, what's our goal? What is our goal? Our goal is to find a Y2 special solution. Remember, Y2 is a special solution, okay? Special or particular. Yeah. Special solution or particular solution. Because when we choose a special solution, we do not need to include constant, right? Because you only need one special solution. When we choose constant, we want to make it general, right? Yeah. We want to make the cover more solutions. In that situation, we choose constant, right? But here, our goal is we want to get a special solution. We don't need to cover many other solutions. Yeah. So for that reason, we do not need to include any constant, and we do not need to worry about absolute value, because two possibilities, we just take the first possibility, right? Yeah. The first one is good for us. Okay. So absolute value. Yeah. Yeah. Because here we just take this form. Yeah. And we believe so this form would work. Yeah. You can verify, right? Yeah. If you feel, yeah. So if we take this form, it may have some problem because we jump from the absolute value form to non-absolute value form. We may, there could be a possible little gap there. Then you just verify. Does the V satisfy this equation? Right? Does it satisfy? If it satisfies, then good enough. Right? Yeah. Because we only need one special case for V. Then one special case for this U. So 2 times U is this one. Yeah. Because after we get a special Y1, special Y2, how do we get a general solution? We have a way to get a general solution, right? Linear combination. From special to general, we take a linear combination. General. Okay? Yeah. And then, is there something you need to worry about when you go from special to general by linear combination? Is there something you need to worry about a little bit? Linear independence. You need to check the linear independence, right? Yeah. Otherwise, you do linear combination on 2 linearly dependent functions, you won't get a general solution. You won't get a general solution. That's the point. Yeah. So there is another step. When we calculate y1, y2 in this way, how do we know y1 and y2 are linearly dependent? Right? Yeah, we need to prove it. y1, y2 calculated in this way must be linearly independent. There, we're fine. Okay. Yeah. So we need to do that. Wait. All right. Find a basis here. Yeah. So in this example, we try to address that basis. Your y1, y2. how do you show your y1, y2 form a basis? If you can show, no, they are linearly independent. They form a basis. Yeah. So here we need to focus on this basis part. Yeah. All right. Find the basis. Yeah. So here, yeah, I change another example. Yeah. Yeah. For the previous one, yeah, a lot of calculation. Yeah. So, you know, I will do it on my scratch paper, so I can prove it, so that I can put it in the video. Yeah. Further explanation video. Yeah. Sometime. Yeah. All right. So here the basis. Oh, sorry. Yeah. So this equation, right? Y1. Yeah. Here we need to find a Y1. Yeah. So you may feel, how do you get this Y1? Yeah. So that is a question. How to get a Y1? Yeah. You need some special method to get a Y1. Yeah. There are several methods people can find a Y1. Okay? Yeah. Later, so we have a chapter, we can use power series method. We can find a Y1. Power series. Okay? Yeah? Yeah. Power series. Yeah? Yeah? It's a, you know, the method you can always apply. Okay? Yeah? Your Y1 could be complicated, but you can find a Y1. Yeah? Using the power series method. All right, so here, this is Y1. Then we want to find a Y2. Yeah. All right. We just use the formula, so we do not go through the, you know, development process. Use the formula directly. We calculate V first, then Y2. Okay. P function and the Q function. Yeah. In the standard form, so P function, Q function, very simple. All right. Yeah. So then we calculate. Yeah. All right. Calculate. All right. After simplification, yeah. So we have like this. All right. Then after simplification, yeah, pretty simple. Yeah. The V pretty simple here. All right. Secant square. Yeah. Then Y2, yeah. Y1, yeah. So then V, yeah. All right. Tangent, yeah. So then simplification, yeah. So Y2 is this. Yeah. Yeah, but the question, how do you know Y1, Y2 are linearly independent? Yeah. Yeah. You need to check. Yeah. Y1, Y2. Why? They must be. Yeah. Actually, the bottom X, yeah, same denominator. So we only need to make sure the numerator are linearly independent, right? Yeah. Denominator, same thing. Yeah. Yeah. All right. So the general solution you can write this way. Yeah. But, yeah. So the question, why these two functions is a basis for the solution space. Yeah. Yeah. So we call, so all the solution we put together, it forms a linear space. Yeah. Solution space. Yeah. So these two functions form a basis of the solution space. Yeah. Okay, all right. Yeah. We need to answer this question. Yeah. All right. Oh, so all right. I just meant, yeah, I didn't answer this question. Yeah. All right. Whatever. I didn't answer this question. I just put a, you know, another further explanation. Yeah. Okay. Yeah. Yeah. Also, actually, I remember I talked about that topic. Okay. Yeah. Number 2. Yeah. Yeah. We need to calculate a determinant. Yeah. Wronskian determinant to check if they are linearly independent. Yeah. Yeah. I remember I talked about that. Yeah. Yeah. I will try to, get that slide. Yeah. Calculating the Wronskian determinant. All right. Okay. To tell if they are form a basis. All right. Yeah. So that's the, this topic. Yeah. I will try to find the slides. Yeah. So talk about Wronskian. Yeah. All right. 8.4. Homogeneous, still homogeneous. Yeah. Remember, in our homogeneous P function, Q function, we say only for special P function, Q function, we can solve the ODEs. Yeah. For complex P function, Q function, we couldn't find a solution. Okay? Yeah. Think about the guessing part. Think about, yeah, you need to guess, you need to use a special way to get a Y1. How can you get a Y1, right? How can you get a Y1? That question still not answered. The Y1. That question still we cannot answer. How to get a Y1? Yeah. All right. Yeah. Although the power series, yeah, later chapters, module, we will learn power series method. We can find a Y1. Yeah. All right. Yeah. But here in this 8.4, we only consider PQ functions, constant coefficients. PQ constant. That's the simplest case. Constant. Yeah. Then we have confidence solving the constant case. All right. Now, AB are constant. Okay. All right. Solution, yeah, inside in the structure here. Then remember the last time in part C of module 1, when I solved PDE, simplest PDE, I mentioned this a little bit. Remember, at that time, I solved 2 ODE. We convert PDE to ODE. Yeah, after the conversion, we solve these 2 ODEs. One is, U double prime minus U equals 0. And we also solve a U double prime plus U equals 0. Okay? Yeah, at that time. And I mentioned we need to solve characteristic equation. So 2 roots, characteristic. Then we can write out the general solution directly. Yeah. Here I need to explain. Now we are at the situation AB. Yeah. So these 2 just special cases of this AB thing. Okay? Yeah. So here inside in structure. Now we need to understand why we can use certain characteristic equations to find a solution in this special form. Yeah. All right. Yeah. So we want to understand here. All right. Simpler version. All right. So here consider y prime. Yeah. So when we start, from something very simple. So then we try to get an idea and try to generalize the idea. Okay? So when we start, we consider first order y prime plus k y equals 0. Yeah. And we know the solution, right? Yeah. the general solution y equals c times e to the negative kx. Okay? Yeah. Decay model, right? Yeah. Yeah. All right. So here you can see the solution. The main building block of your solution is the E function. That's the main building block. Okay? All right. So E function. So E function here must have some special property. E function. Okay? Does it give you some insight for the current ODE? Yeah. E function is very special. Okay? Yeah. Can we use the special structure of E function to help us find the solution? Yeah. Right? Yeah. Try. So here. Yeah. Now let's try. Think about how about the solution of this equation could be some E function, e to the certain parameter. Yeah, certain parameter unknown. At this point, we don't know what parameter should be used. So we put a lambda to be determined. That parameter should be determined. E to the lambda x. Here we have freedom to choose different lambda to make this function possible solution of the original equation. That's the idea. Okay? Yeah? Yeah? Because this form make first order work. Now, at least we try this E function. Is it possible? It can also make the second order ODE constant coefficient ODE work. At least we try it. Yeah? Yeah. Try the idea. All right. With lambda, yeah. Now, y prime, lambda times e to the lambda x. Y double prime, lambda square times e to the lambda x. Okay? Let's go back. All right? Yeah. When you go back, you can see the E function is the common factor of the all three terms. You can factor it out. E function. Yeah. After you factor it out, can you cancel out this E function? Both sides cancel out. E function. You cancel out. Is it okay? Without any problem? Yes. Because E function can never be zero, right? E function can never be zero. It's a non-zero term. Can you cancel out non-zero term both sides? Yes. Non-zero you can cancel out. If it could be zero, then you cannot cancel out. How can you cancel out zero both sides? You cannot. But now, because E function can never be zero, so we can cancel out without any problem. All right. After cancellation, the remaining part inside parentheses we call the characteristic equation. That's this function. That's one. Yeah. Last time I mentioned when I calculate these two ODE, I talk about characteristic equation. Okay. Here you know why. Okay. Yeah. Here you know why we use characteristic equation. Okay. Yeah. Here the story. Yeah. Here. All right. Yeah. Yeah. Or auxiliary equation. Yeah. But most time people use this name. Okay. Characteristic equation. Most of the time. All right. You can easily solve that quadratic formula. Yeah. Two possible solutions. Yeah. Two possible solutions. Yeah. Then we do discussion. Yeah. Because these two possible solutions, yeah, we need to consider the cases. Yeah. Yeah. The first case, two distinct real roots if the part inside the square root greater than zero. Two distinct real root. In that case, we can write the solution. Okay? Then the second case, a real double root. No. Double root, okay? Square. Real double root. Then a squared minus 4b must be 0. That's the double root case. A real double root. Okay? Third, complex roots. Now, a squared minus 4b less than 0. So there are these three cases, and we need to write out the solution form for these three cases. Yeah. All right. Yeah. I try to complete these three cases before the class. All right. Solutions for three cases. Yeah. First case, second case, third case. All right. Yeah. A specific form like that. The first case, we can write out the y1, y2 directly. y1 e to the lambda 1x and y2 e to the lambda 2x. Very easy. Straightforward. Yeah. All right. Then, second case. Second case, also easy, but you need to do things slightly different. Because in this case, your characteristic equation only has one double real root. That means your characteristic should have y1 squared equals 0. Okay? Yeah. Your characteristic equation like this: lambda minus lambda 1. y1, y2 equal, so square. There is a square here. Okay? Yeah. But when you write the first equation, you can use y1. Yeah, because you have a y1 you can use. So the first equation, because y1, y2 equal, this. Yeah. So the first equation, you can use your y, negative a over 2, so that lambda thing. Okay? But your second equation, you don't know how to write, your second solution, y2. y2, so the y2 is in this way. y2, x times the y1 solution. X times the y1 solution. You get a y2. Because you can verify it, okay? You can, plug in into the original ODE. You can verify it, okay? Yeah. So also easy. All right. Then let's look at the case number 3. Case number 3. This time you have complex root. See, I times because b is greater than 1/4 times a squared. Yeah, b greater than that. Okay, divided by 4. So so you have y1, y2 form. There is an I here. But when we write a y1, y2 solution, we don't want to include I, right? Because in the real world application, we want to avoid I representation in many situations, but not all. Because in electric circuit, many times we need to keep that I. All right. So here, we want to avoid I in our solutions. All right. So here, let's write a simple. Because this rule, too heavy. Not neat. So we use this way. Introduce omega represent this big root. All right. So in these two forms, then we can write a y1, y2 solution. y1. So here, omega. So y1. All right. E part, you have E part. E part corresponds to the real part of lambda 1, lambda 2. Lambda, you have a real part. Negative 1/2 times a, that's the real part. So the real part, you use it to write E function, E to that real part times x. Then imaginary part, omega, right? Imaginary part, you use cosine sine. Cosine omega x. Okay? That's y1. y2, the same e part. Okay? Same e function. Then sine of omega x. Then you don't have I. Yeah. So cosine sine. Yeah. So you do not use I-related expression. Yeah. Yeah. The way to do it, remember last time on the slide, I wrote how to use the linear combination of these two complex numbers to get rid of I. Yeah. So that thing, yeah. So here we don't need to repeat. I did similar thing before. Yeah. You just use similar idea. Yeah. So here we just give you the final solution forms. Yeah. So all these three cases, you can write out the solutions. Y1, Y2. Yeah. But at the end, when you write general solution, you need to use C1, Y1 plus C2, Y2. All right. Another question. Linear independence, right? Yeah. Linear independence. Yeah. How do you know Y1, Y2 are linearly independent? Okay? Yeah. 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 All right. Yeah. So here we use that. Yeah. All right. Yeah. Yeah. So here I try to explain. Okay. Yeah. How to explain how to get rid of I. Yeah. Yeah. But we did that before. Yeah. Yeah. Adding together. Yeah. Yeah. So now after so far at this point, yeah. So we explain all those things, yeah. But one thing we skip, we haven't explained. Show you why Y1, Y2 are linearly independent. So that part at this point we skipped it. Yeah. But that part is important. So I need to find a way to bring that part back. Yeah. Bring that part back. Yeah. So that part, the basic idea, I want to cover in class. Yeah, because that part is important. Yeah. Not in further explanation. Yeah. Further explanation, usually I want to cover important method or concept. I just want to cover routine calculation. Routine calculation, I put it in the further explanation. But important concept and the method, we need to do formally in class. Yeah. But checking independence, there is an important method. So I want to talk about in class. Yeah. 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 Next time I will talk about that. Yeah. Let me see if I. Yeah. So that's the end. Yeah. So when I see this, that's the end of this part A. Yeah. So next time we will go part B. Yeah. Yeah. But the first thing is I need to talk about linear independence. Okay. Yeah. 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 So we cannot delay too long. Yeah. Because that's too important. All right. So that's it. So this week, yeah. This week I do not plan to give you a new assignment because our big assignment, homework number 1, that's the most important one. So why I give you another assignment? Quiz. No. I delay the quiz after you complete first assignment. Yeah. So spend all your time on this homework assignment. Okay, this week and the next week. Yeah. All right. Yeah, that's it.